Hi, it's Paul Anderson, and this is Science and Engineering Practice 2, Developing and Using Models. Models are important in science and engineering for a couple of different ways. In science, we use models and modeling to explain phenomena or to share an understanding of how the world works. In engineering, we use it to analyze systems, and lots of times we'll do simulations or build models to see how a design is going to perform. And so before we get to models, though, I really want you to understand what a model is. And so I'm going to start with a couple of questions. So first of all, in this drawing right here, which square do you think is darker, A or B? Pause the video if you want to take a look for a second. And of course, it's a trick question. They both are going to be the same level of darkness. We could even reconstruct this. So if we take those two squares, A and B, and rebuild the optical illusion, watch carefully, all of a sudden B gets lighter. And so we're tricked by the shadow of this cylinder. And so that would be a mental model you're using to figure out which of those is darker. Let me come up with another question. So this is a diagram of the Earth and the Moon. The scale's okay, but they would be way farther apart. You can see that one half of them is lit, and then I've put the North Pole on the Earth so you can know where that is. So if you were standing here, if you were to stand right here on the Earth in the northern hemisphere, what would the moon look like as seen from the Earth? So if you want to take a little bit of time, you could pause the video. And the right answer is D. If you miss that one, then your mental model might not be working. Your mental model of the way the Earth and the moon and the phases of the moon work might be ineffective. And so to solve problems, to understand the world, we use mental models. And they're great. That's the way that you work. The problem with mental models is that they're just yours. They're yours alone. They're inside your brain. They're unstable. They're idiosyncratic. That means that they're going to be different in every individual. And also, they're lots of times incomplete or ineffective. And so the mental model is not what we're talking about when we're talking about modeling. What we're talking about are physical, conceptual models. And so those are clear. They're shared by everyone. They're external, and they act as an analog. In other words, they're an analogy for how phenomena work or how designs work. And so those analogs can basically be structural. This would be structure of DNA in a model. We haven't seen DNA per se. We can't see it. It's too small. But we can build models that explain how it works. It could be behavioral, a model, how it's going to perform. So this right here is going to be ants foraging. Or we could look at a wing in a wind tunnel. That could be a behavioral model. Or we could look at its function. So these are going to be the lines of magnetism around the different fields of a magnet. And so these are different analogs. And then we can manifest those analogs in a number of different ways. And so you could make a model that's just simply a diagram. This was a diagram created by Charles Darwin when he was trying to explain how speciation occurs. And he draws this branching diagram from a common ancestor. Or this could be a computer simulation of a protein. This is myoglobin. We could use an analogy as a model. For example, if I understand how fluid moves through a hose, I can use that to explain how blood is going to move through the vessels, or I could use just a mathematical model. So this could be the ideal gas law. It's simply a formula that explains what happens as we increase pressure or decrease volume or increase temperature. We can understand what's happening. Or even a simulation. This is a simulation of osmosis as water moves through a semi-permeable membrane, a computer simulation. These are all different types of models. In engineering, we use models lots of times to test a design. So this crash test and the crash test dummies and all of the material that we're getting back from that is allowing us to see how well a design works. We can also use models to build designs. And so we can use computer-aided design software or CAD software to build material, and we can physically build it now. So this would be a three-dimensional printer, 3D printer where we can print materials. We could actually print like this part of a motor, and then we can see how that performs. And so again, models are going to be physical, shared, clear understandings, and they're really the manifestation of mental models. And so the goal in science education is help students to develop models. And they do that, first of all, by constructing drawings and then representing phenomena. And then finally, we're going to use those models. We can use models through simulations, and then we can also test designs. And so let me talk about a nice progression for this. In other words, going back to the analogy of throwing darts at a dartboard, we want our students from the time they begin education to start developing and using models. And we want to refine those through the years and get better and closer to the bullseye. So when they're seniors in high school, they really are good at using models. And so what would be a good way to start this in the elementary? Well, you could show them a picture of an insect and have them draw an insect and then draw the parts of an insect. Or you could give them a demonstration and then have them draw parts of it. So for example, a car on a ramp, if we're studying how fast material moves down a ramp, make sure you get students right away constructing drawings. Drawing water and how it warms up during the day and how light affects plants. And so the more drawing we can do earlier, the more model building we can do earlier, the better. As we get older, we can start to refine those models, and so we can represent actual phenomena. And so now, as we get into middle school and onto high school, we could label forces acting on that same drawing. And so this would be a force diagram. As we move on, we also want to start using simulations. And there's a number of different simulation softwares out there that you can use to build models, like Google SketchUp is an example of one where you could build designs. But if you want to do scientific modeling, a great choice would be NetLogo. You can download it for Mac and Windows. And basically they have a number of different simulations. So you can simulate phenomena and then you can kind of interact with that. And so this one right here is a NetLogo simulation where you're looking at wolves and sheep and then the food for the sheep and how they'll move over time. This one is a video I created of ants. And so basically what you have are ants that are foraging on food, and then when they pick up food, they're going to bring that food back to the nest, which is in the middle, but they're going to drop off chemicals as they move back, and that's going to diffuse out. And so again, this is simply a computer model that shows how ants feed, but then students can interact with a lot of the inputs, and so they can play around with it, and they can see how that model is used. And they can also create models of themselves. If you know any kind of programming, you can produce these really powerful models in NetLogo. And then finally, we can test designs. And so the best way to really figure out the importance of testing designs is to actually do competitions. And so mousetrap cars is something that I've done before. Basically, you're creating a car that can move just through the power of a mousetrap. And when you give students a question or a problem, like how can you do that, and competition, they're going to come up with ideas that are simply amazing. And so not only are they building models, they're building physical models that they can test. And so they're really doing engineering, they're doing science, they're putting it all together. And so what are models again? They're really a physical manifestation of this mental model that we can all share, and we can use that to explain phenomena and also test designs. And I hope that was helpful.